Welcome everyone to MAREA on tonight's topic on advanced battery technology. I'm Tom Kirshner, a board member of MAREA. MAREA is the Mid-Atlantic Renewable Energy Association. We're a 501c3 nonprofit dedicated to educational issues on renewable energy and sustainable living topics. As I said, tonight's topic will be advanced battery technology. Coming up in May 28th, we will be hearing from Doug Copeland of Atlantic Shore Offshore Wind. We heard from Doug a couple years ago. He's going to give us an update on his project, their project. They're developing 1,500 megawatts of offshore wind energy. That's enough to power 700,000 homes. That'll be May 28th. And then in June, I don't have the exact date, but last Tuesday of June, we will have a speaker on the dark sky initiatives. This is, we'll be talking about the initiative to reduce light pollution. And we'll be talking about the advantages of that and the disadvantages of having light pollution, not only for your ability to see the sky, but how it affects wildlife and plants, etc. So that should be very interesting. And as soon as Chuck comes back, he will be introducing our speaker for tonight. Chuck, you ready?
Yep, I'm here. Greetings, everyone. It's my pleasure to introduce Derek Hall tonight to give us a presentation on what's new in battery technology and electrochemistry. So Derek Hall is an assistant professor from the Department of Mechanical Engineering at Penn State University. His research activities focus on fundamental and applied electrochemical engineering problems important to the energy industry. His current research projects focus on thermally regenerative batteries, electrocatalysis for redox flow batteries, metal solution interfaces, power plant water cycles, and new electrochemical sensors for gas pipelines. And in addition to all that, Derek's going to give us kind of an overview of what is new in electrical transportation sector, if I'm not mistaken. So without further ado, Derek, I'm going to leave the floor to you. And if you could share your screen, we could get started.
All right, great. Thanks so much, Chuck. Can everybody see my screen? Looks good. Okay, I'm going to take no complaints as a success. All right, thanks everyone for joining me this afternoon or this evening. So today we're going to talk a little bit about batteries and how they're impacting our lives and how hopefully that will be changing moving into the future. But before we get started, a little bit about me. So my laboratory is the Electrochemical Engineering lab for the energy and the environment. I'm actually from Penn State as far as my background goes. I got my BS and my PhD there. Started with a postdoc. I went off to ORISE, which is an organization that provides postdocs for the National Energy Technology Laboratory. And then I came back to Penn State. So what we do in our labs is we focus on electrolyte interfaces to solve problems in the energy industry. So what that really means is essentially this is what this looks like. Nice cartoon. We have an electrode, usually a solution, or usually water with some sort of ions in there. And we want to better understand and tune this interface to benefit a wide range of technologies. So some of those we're going to talk about today, like batteries, but there are other ones such as fuel cells, hydrogen electrolysis, water desalination, sensors, heat exchangers. All of these have these electrolyte interfaces in them, and they all have a unique set of problems. And that's what we work to try to resolve. So our toolbox for doing that is electrochemical techniques. We also do some computational modeling and material characterization. But it all really focuses on trying to understand what's happening at this interface and can we either speed things up or slow things down depending on the application. So some of the areas where we use these techniques and these tools, around two. One are energy storage devices, which we're going to talk about today, and the other are electric power systems. So in the energy storage devices, our group works on making new battery materials and new energy storage processes, which we'll touch on at the end of the talk today, but also in some more conventional energy power systems like making new sensors and improving steam cycle chemistries to keep the current infrastructure running safely. So why electrochemical engineering? That's sort of a new term, and it's becoming more and more prominent as batteries and other technologies like that are emerging. Well, I think electrochemical engineering is important because many of the new electrochemical devices that we're going to talk about today can help reduce carbon emissions. And so if you kind of look at our goal for reducing carbon emissions is where we are now, which is shown in this cartoon, we essentially need to cut it in half multiple times in order to get to more reasonable conditions to mitigate the worst effects of climate change. And so one of the big slices in our current emissions are carbon emissions related to transportation. And here, batteries and hydropower vehicles can have a powerful role if they're further developed. Another one is the carbon released from our electrical grid. And the last one is it can also help to improve energy efficiency through a number of different ways. So there are certainly other things that need to happen as well, but these are a few that can be helpful. As I am a professor, though, first I have an energy quiz for all of you, for any energy enthusiasts, to see how well you know your personal energy use. So to simplify this, one problem with working in the energy field is there are so many different units to quantify energy, right? If you're eating, it's calories. If you're heating things, it's called thermals or therms or BTUs of natural gas. If you're talking about electricity, it's kilowatt hours. So we're gonna unify this in a fun talk, right? So we're gonna call it a new unit called D, right? We'll make it simplified. It takes about 2,000 calories is roughly the average calories recommended for a person to fuel themselves for a day. So we're going to call this 1D, right? Basically the same amount of energy it takes to fuel each of us in a day. So the first question is, how much energy do you think it takes to run a 100-watt light bulb for an entire day, for 24 hours straight? So a 100-watt light bulb is essentially an incandescent light bulb, right? It's not one of the more efficient LEDs. So think about that. Do you think it's either greater than or less than the same amount of energy it takes to power you? Well, this one's sort of a trick question. It's almost exactly the same, right? So to run one of these 100-watt light bulbs all day, it's about 1D, right? So the next one is going to get a little harder, right? So the daily usage, daily electricity usage for a U.S. household. So this doesn't include heating usually. Some do have electric heat, but most of them are still fuel based. So I guess, do you think that's greater or less than 1D? Right. So usually we do the order of magnitude test with engineering, right? Is it 0.1D? Is it 1D or is it 10D? Right. So this is actually 13D, right? So it's about 10 times more. This is basically than what you would have in order to power yourself. Right. On to the next one. A gallon of gasoline to go about 18 miles, which is roughly the average commute of a person for a day. This one's 15D, right? So it's pretty close to how much you would use to power your house. And the last one, the energy in the natural gas needed to heat your house for a day. So this one's a little bit bigger. It's 31D, right? So now if you could think about all the different things that we do, you can add these up, and that sort of gives you a sense of just how much energy we use and how amazing energy engineering is as far as taking what the same amount of energy it would take to power you and how many people it would take to do that same amount of work, right? How much energy would be expended to do the things that we do on a daily basis? Okay, enough with the quiz. So part of this talk is to give a little history into batteries and where they came from. I always find it fascinating to think about where our technologies come from and how long or not long they've taken to get to where they are. So the first fact I want to give you is that batteries have evolved dramatically over about 200 years, which is when the first battery was invented, right? So Volta, who was trained by Galvani, made his voltaic pile, which is the first known battery that we know for sure. There's some suggestion there may be others, but this is the first known one, right? And this came around in 1800 exactly, right? And then about 60 years later, the lead acid battery, and this is one that's still used today, right? There's more engineering goes into it, but the first version of this came out in 1859. So that's still pretty young. And then we go on to the modern lithium ion battery, that we're mostly going to talk about today is about 1970s and 1980s. So I think what's surprising to me is that this is only 200 years old, right? So that's only a few generations uh, of people working on these devices and just how widespread they are. And just to give you some more context on this, so the steam engine, the combustion engine, are two others. They're also relatively new, right? The steam engine's been around for about 300 years, whereas the combustion engine that we see in most of the ICE or internal combustion engines is about 250 years old. So of the three major methods that we have for producing, or I don't say producing energy, but for utilizing energy, batteries are one of the youngest, and in some instances, very complex. So some other interesting things about batteries, right, is the more we make of one kind, the cheaper they get. So this type of technology, like cell phones and a few others, the more we make of them, they get into this sort of positive feedback loop that helps get them cheaper, right? So you deploy more of them, the prices fall. That makes more options to use them in other markets that would be harder to work at that price point. The demand increases in each of those, which leads to more development, which drops the price further, which allows opening to other markets, right? And the batteries are a great case of this. So when you look at them, the first lithium ion battery that was made, right, in 1992, just after when they sold it, extremely expensive. And then this progressively has been decreasing in cost every year leading up as we increase the capacity of what we're making, right? So it's dropped dramatically in that period of time. And so that, and you think of the first market that we remember lithium ion batteries in, these were first produced by Sony, and most of this was in personal electronics. So they were the Walkmans, moved into laptops, electric razors, small things that were portable in the household. But as they got cheaper and cheaper, this became more likely to be used in electric vehicles and other markets and other ones that we'll be talking about, like large scale batteries. But another interesting thing to think about is electric vehicles were actually one of the first um, types of vehicles that were being made. The first electric car was actually developed in 1832, right? And if you think about that, when batteries were actually developed, right? 1800 was the first battery. Within 30 to 40 years, somebody designed the first electric vehicle. And so this one was a bit clunky, but then they eventually became very popular because they were much safer, much easier to start than the conventional internal combustion engine, right? They still needed cranks. And the Model T car that's well known in the US hadn't even been invented yet, right? And so electric car vehicle sales actually took off right up until the Model T started. And actually, the first electric hybrid, right, which is an ICE mixed with electric vehicle, this was actually made in 1901. So all of the technologies that we're talking about that and has come out in the news, these were actually invented in the first versions of them a long time ago, right? But as with most technologies, cost is really important, right? So with really cheap gasoline and with the Model T, it took over, and these electric vehicles with their limited driving range just never take off, and they sort of fizzled up until today. All right, so enough with the history lesson. Let's talk a little bit about modern batteries and how they work in electric vehicles. So electric vehicles, the new ones that we're seeing, have a lot of advantages, but there are still a few new challenges as far as using them for personal transportation. So one of the main advantages in an electric vehicle is that the number of components going into the powertrain system are actually much, much less overall, right? So because the ICE powertrain is based on combustion, there are a lot of supporting systems and a lot of moving parts, both fluids, to try to maintain the temperature inside it and to get it to work properly. So this simpler system with less components and also cheaper components going into it as the costs drop down provide a lot of opportunities to simplify, and by some projections will lead to electric vehicles being a potentially lower cost than ICE cars once they get more production. So if these keep getting produced, they should end up getting to a lower cost. One, just because there's less components, and two, because there will be less maintenance and also less fuel costs over the lifetime of the vehicle. But the main deterrent for that at this point is the cost of the battery pack. And most of this is due to a lack of production, right? So as production of these battery systems increases, the cost will start to decrease. And I think the current projections are that parity with ICE vehicles will hopefully occur within the next 3 to 5 years. And then after that, they may be cheaper. Again, there will be other things, right? The ranges will be different. The use cases may be very different, but at least as far as which one is the most cost effective for purchasing, there's a lot of evidence to suggest that these electric vehicles will be much cheaper over time. Another benefit is that electric vehicles provide an opportunity to significantly reduce the emissions related to personal transportation. So an electric powertrain vehicle, an internal combustion engine produces a lot of emissions on a locally that are very difficult to extract or to try to clean up, especially when it comes to CO2, right? Trying to come up with a CO2 capture system for every ICE system out there can be very complicated. But if you switch over to something like an electric vehicle, where essentially the power generation is centralized to one location, wherever the electricity is being produced, that provides an opportunity to create a clean source or to clean up that source of power generation, to convert it into electricity, and then provide that electricity to the electric vehicles to allow that transportation to occur. So if you imagine a scenario where most of the electricity in a region is produced by renewable energy, then that means the emissions from an electric vehicle will be quite low. However, if we stay with using things like fossil fuels, such as coal or natural gas, the emissions from the electric vehicle, due to the energy that's being, the emissions being generated from transporting that electricity, then they will still have some emission tag with them. However, there are a lot of options to be able to clean up those emissions at the power plant source, right? Rather than having, right, think of it as millions of power plants distributed everywhere, you can centralize them a bit more where they are and focus on cleaning them up where they're being produced. So there's a lot of opportunities to reduce the emissions by moving to electric vehicles. It essentially offsets the problem to another source, which is easier to address. However, it's important to mention that there are some new challenges that will come up as well, right? So with these new battery packs that are being made, there again, the same problem of making a circular economy, right? If there's waste at the end when the battery is over, how do we retrieve the materials inside that battery? And where do we find the materials in order to build those battery packs on a larger scale than they've been used before? So this has to do with sourcing of the copper, cobalt, nickel, carbon, all of the materials that go into that battery pack. If we are to replace a lot of combustion-based vehicles with battery packs, we have to identify where are those sources going to be, because that's going to be a considerably larger amount of material than has been used for most of those in the past, right? And recycling is always critical. We can't make them and expect them to be single use. They will pile up. So learning how to take them apart and extract those valuable resources is another important component, right? So there are definitely some strong advantages right away from adoption, but there are also some new challenges to address in the long term. Okay, so similar to the personal electronic battery packs plot that I showed before, where you saw the prices of the first lithium-ion batteries being quite expensive. Well, these electric vehicle battery packs are quite similar. So they benefited from some of that production, but there's still a lot of new aspects of putting many packs together that increase the challenge a bit. So if we look at electric vehicle pack costs, since the modern electric vehicles have started being produced, you see a similar curve, right? The prices start fairly high, but they've been consistently dropping year by year as we've become more proficient at developing these battery packs. And if you look at the projections into the future, right? So you look at where these costs are coming, right? Again, they show that the electrode materials, some of the pack design, and a few other costs going into it will start to fluctuate over the years, but they're expecting to drop even further as it moves on. And one interesting thing is that there's been a lot of forecasts. So anytime someone says they know what's going to happen in the future, you shouldn't believe them, myself included, right? I'm just reporting what someone else is discussing here. But what's been interesting about solar, wind, and also batteries is that these forecasts have been consistently over or underestimating how fast the prices have dropped. So hopefully these trends continue. And that was one of the goals of this study, is essentially saying, well, here's where the forecasts have been. So far, it looks like we are starting to um, decrease the cost of these batteries faster than expected. And if we went back in time, similar analysis has been done for historical records showing the same thing. So what we're essentially saying is that they are dropping, and it seems like the costs are dropping much faster than expected. Not as fast as we would like, but still faster. So that most of those enhancements in cost reduction have come from increasing production capacity, improving the supply chain, but there are also still some significant gains to be made from improving the chemistry or the type of lithium-ion battery that we're using. And so these are the conventional lithium-ion batteries that we've been using. These were some of the first ones developed by Sony, and so they have these fun acronyms to describe each of the chemistries. So this is lithium iron phosphate, and others that some depend more on cobalt, nickel, and magnesium. So these rare earth and critical minerals, some have more of them and they tend to be higher performing, while others have much less of these critical minerals but still work, but they don't perform as well. And what we mean by performance is their energy density. So what this plot shows here is the energy density for a bunch of different modern battery types. And what energy density means, is that essentially the more energy density you have, the more miles you can go per charge. And if we reduce the cost of one of those, that means one, less batteries that you need on the vehicle, and two, it can also correlate to how much further you can drive if you stack the car full of these. So this kind of gives you the range of the lithium-ion batteries, and these would be the ones that are in most of our personal electronics and a few of the electric vehicles that you're using. But there are some other newer chemistries that are being worked on in the lab, and there are also some companies selling early prototypes of each of these that have the potential to increase the energy density much, much further than the current lithium-ion batteries that we're using. So some of the ones that are worth noting are the solid-state batteries that have come out recently and gotten quite a bit of press. So what's encouraging about them is that their starting energy density is much, much higher than all the advancements we've had in the lithium-ion conventional batteries. So that has nothing to do with cost at this point. They're still more expensive. But if you look at the materials that they're using, there is the potential for them to get much, much higher in the future. So there are still some limited experimental results that are showing that these are possible, but they're still not ready for market. So there's a lot of interest and excitement around these new chemistries, particularly ones using lithium metal or solid state chemistries where they provide an opportunity to have an enhanced safety and larger energy densities. But there are still a lot of issues to work with them before we will see them on a larger scale. So every time we make a change like this, you have to go back and work on your production and work on driving the costs down. But this battery field is getting more and more populated. Another interesting one to note is the sodium ion battery. So there are some commercial versions of this, and even though the energy density is quite low, what's promising about these types of batteries is that they offer different materials to do a similar purpose, right? So this allows each of these battery types, depending on the performance needs or cost needs, there may be some of these battery types will work in one area versus some will work in the other, right? So think of them as like different styles of cars, right? If you want a high performance car that can go really far or do a particular job, one of these more expensive but better performing batteries might be applicable. But if you just want the cheapest, most reliable way to go a few miles, one of these other batteries might make more sense, right? So as more of these get developed and become commercially viable, we might start to see more of them showing up in some technologies, whereas others may start to dominate in technologies that have higher or lower performance criteria. So it's a really exciting time for battery research with all of these different options. So what does this look like in the near term future for our personal transportation? Well, one interesting thing to think about is the average commute time for people in the US. So this was a recent survey going through and looking at the typical commuting times and behaviors of people in the US for a wide range of places, right? So this is between the city, the country, and you can break down and see what they look like for each of these different regions. But overall, most of the people in the US have commute times that are less than an hour. So if you translate that to distance, that usually means that they're within 50 to 60 miles of their location. And those less than 15 minutes, they live within a few miles of their location, right? And so if we think of what we use for transportation now, ways that you can think about this is look at the different options that are available, right? Some of these small electric vehicles that you may see if you're in a city, like electric scooters or electric bicycles, they're really great for going very short distances. The costs are very low, maintenance is very low. There's minimal restrictions. More and more people are adopting them, which you can see in the streets. And I definitely see this in our location here. There's a mountain of these scooters depending on where you go and how popular it is, right? But if you're further out, you're starting to get to these longer times or further away. These electric vehicles, especially if they become cheaper than combustion engines, they're going to be the easiest and lowest hanging fruit for a transportation need into these larger commute times, right? However, there are still going to be a lot of applications and some needs where a conventional ICE vehicle will still make sense, at least in the near term, right? And so these were things where you have heavy weight requirements or really long distances that you need to drive. I mean, there's certainly ways that we can do this with batteries and fuel cells, but it's really if you're committed to it. I mean, they will still work. It'll just take more time, right? But for many people, they'll take the path of least resistance. So there's a lot of evidence to suggest these will still be around for some time, unless there's something else to push them out. But more and more, these options will become more attractive, especially as the costs go down. All right, so let's switch gears a little bit. That's sort of an overview of where we are with electric vehicles. Let's talk a little bit about household battery systems. So think of that wheel that I presented before, right? As the costs drop, more markets become available. And another one is backup power for household systems. So this is another trend that's taking off where we can get battery packs to help with supplying building electricity needs. So each of our buildings, there are two options, right? If you're buying solar panels, you can provide with a battery. This is typically $25,000 to $30,000 for a pack. Again, this is for the average house, right? If you have more electricity consumption or a larger house, prices go up. If you have a smaller location or a smaller energy profile, these will go down. If you just want the batteries by themselves, right, for backup power to replace like a generator, they're about quite similar, right? They're typically about half to two-thirds of the cost, right? So most of the cost in one of these microgrid systems for a house is still to the battery pack. And the reason for that is it is one of the newest technologies, right? And we're still working on optimizing it. Solar panels have gotten much cheaper. We'll show a plot on that later. But they are already getting very, very cheap, right? So batteries are still in their early years as far as their cost. And so what this will do is if you buy something at this price point, this will essentially allow you for a typical household electricity use, which is about 30 kilowatt hours per day. This will give you an opportunity to create a microgrid where you will be able to collect power during the day, charge your batteries during the time with excess power, and then be able to use that later in the evening and night when the solar panel isn't available. Additionally, if there's something like an energy upset, right, or if there's a blackout where the electric grid is not in place, if you have backup power for this price, you can essentially get about a day's worth of electricity from those battery packs. But because it's new, there are still quite a few different sources, right? And this will impact how much or how little energy you can store, right? So what these battery pack systems look like for a household, here's two different variations, right? So this is the Tesla power block, right? But then there are also other market options where you get more of the classic lead acid type design that you can use for your residential power pack, right? So you see in the lithium ion here, that profile or the space that's taking up is a bit smaller. As you move to other options, it increases in size a bit. But what these can provide to you are they can help with providing round-the-clock power. So by installing some of these, if there are any power upsets or or stoppages in your electricity generation, you can use these to help keep the lights on. It can also help mitigate any costs if their electricity prices are rising or they charge different prices depending on what time you use them. You can use these battery packs to sort of offset your use for different points in the day. It can also provide you some monitoring capabilities where if you have a solar panel installed as well, you can watch how your energy consumption varies, right? So by having a device, it's sort of like the same with our phones, right? If we see what our energy level is at, that shows us how often we're using our phone and when we need to recharge, right? So it brings us more in contact with our energy use in our house. And if you have that combined with a generation source that provides you some energy self-sufficiency, right? So if you have the solar and the battery pack, that allows you to go much, much longer without the need for an electric grid or that support, right? So there's a lot of benefits for this for residential power, but those benefits really depend on where you live and what your needs are and what your current relationship is with electricity. And to give you some context on that, that sort of so can be seen here in these adoption trends. So what I'm showing you here are the power capacities of small scale battery packs. Most of these are coupled with some sort of solar array. And you can see the adoption rates depending on the location, right? So in Hawaii, where they've had more upsets, there's actually this enormous surge in small scale battery adoptions for residential space. So most of the houses, I think it's like 96% of all houses that install solar in Hawaii also come with an adopting battery pack, which is why it's quite large, right? But then you get to other areas where perhaps they have less outages or there's policy restrictions that residential value starts to drop off. But this is another market space for this battery technologies that's starting to take off because it provides some benefits to the consumer. And that if you're interested in this, you can also look at those same plots that I showed you for personal electronics and for electric vehicles. There are similar plots and data that you can find for small scale battery storage applications as well. So the initial costs for the first models were a bit costly, and they are starting to drop quickly as these adoption rates increase. So yeah, again, another maybe less on the radar for some, but another interesting application for batteries in your personal life. Okay, so the first two topics that we talked about, electric vehicles and backup power for your house, are two that are more likely to hear that are coming up in the news. And those are the two that are taking off the quickest in terms of early adoption of these modern batteries. But there's another type of battery that's coming into play now that these are getting cheaper. But this is the one that requires the lowest price point to be successful. So this will be the one of the later ones to develop. And these are grid scale batteries. So essentially battery power plants. These would be batteries the size of a building that work with industrial or large scale solar in order to help complement them and act together like a power plant to replace some of the coal-fired power plants or natural gas power plants that we've used in the past. So this portion of the talk, I'm going to discuss a little bit about the state of the art with these batteries. And this closer ties into my research area, which is trying to provide battery storage or energy storage on a large scale. So some of the motivation that's driving large scale battery adoption is that the energy landscape of how we produce electricity is changing quite a bit. And so we're going from carbon intensive sources to renewable energy sources. And unlike the other cost profiles that I've showed you before, here's a survey of the different costs for 4 different types of renewable energy over the past few years, right? And solar panels are dropping quite quickly, right? So they started out to be very expensive. But as we made more and more of those, right, as that production increased, the cost started to drop dramatically. The same is happening for concentrated solar and also for offshore wind and onshore wind. Oh, got them backwards there. And what this gray block represents are the prices producing electricity using coal or natural gas plants. So you can see that depending on the date of the news article we look up online, right, there is this case, you can make an argument that solar is too expensive and it shouldn't compete with coal or natural gas. But as we start to increase the production, that starts to change, right? And now we're getting to the point where, depending on the location, these renewable energy applications are actually cheaper than any fossil fuel based method for those locations, right? And this has happened for onshore wind in some locations, and also for photovoltaic based solar energy production. But this adds a new problem, right? So in many instances, the supply of this electricity, especially solar, happens exactly when we don't want it, in the middle of the day, when our demand or the use of electricity is actually lower. So most places in the US, demand for electricity is highest on our just before our commutes or during our commutes into work, and right after when we get home on the classic 9 to 5 schedule, right? So imagining most of the office workers getting home at 6, turning on their tea kettle or their television, and we get this spike, right? And then as we all go to sleep, it goes down. Most of the solar gets produced in the middle. So what this is an energy storage problem, right? If we're able to collect this solar energy or this electricity that we're producing in the middle of the day, offset it by a few hours, or then we would be able to help address a lot of this need that we have, right? And you don't worry about all of these names, but where this problem has been recognized, and there are many, many different methods of storing electrical energy, right? So there are the electrochemical methods, like the batteries that we've talked about. There's a new type that we'll discuss later, flow batteries, but there are also electromechanical methods, which include pumped hydro, flywheels, conventional capacitors. There's chemical storage methods, thermal storage methods. So there are an enormous number of options when you no longer have to put it into a transportation vehicle. So some of our research is to try to figure out which of these options is the most flexible and the most cost effective for trying to meet this demand. So what's the scale of this problem? Well, for large scale energy storage, again, this is excluding electric vehicles, excluding the any backup storage requirements, right, for blackouts and things like that. The Department of Energy predicts that this will go up to about 200 gigawatts of needed energy capacity, storage capacity by 2050. This is just to accommodate for replacing our fossil fuel-based systems with renewable systems. In particular, if you look at most of what the storage is today, this is pumped hydro storage, so it's long-term 12-hour storage, right? More than half a day is of how much storage you can have. But what we really need a lot of is going to be this 4 to 6 hour battery storage, right? So basically taking something from the middle of the day, shifting it into the afternoon, and providing that additional power when the sun starts to set. And so these are the two areas that are expected to grow the most, this 4 to 6 hour storage window, and to some extent this 8 hours. So 4 hours considered, once you get to 6 to 8, that's more long duration energy storage, whereas 2 to 4 hours still on the shorter duration end. So what does 200 gigawatts look like? Well, a good way to describe this would be equivalent to 80 billion iPhones, right? So everybody, almost, there's about an iPhone for every person in the US. That's about current production, right? That's about 300 million. We need 80 billion approximately to satisfy that. So that's just to give you a sense of how many more batteries we need to satisfy this market. It's just an enormous amount, right? Another way to look at this would be in cars. So this would be 10 million Tesla vehicles, right? Which is still a big number. But what's interesting about that is that think about how many cars are in the US. There's about 300 million people, most of which, there's about one car per person. So that actually shows you how big this electric vehicle energy storage market is, right? So if you put those two together, this is an enormous amount of batteries that need to be produced, right? So even though we see batteries in our laptops and our phones, these new batteries are so much larger, right? So this is an image or a cartoon of the size to take up the world's largest battery. And we would need 800 more of those just to satisfy the US, right? And there's only one or two right now. So this is just a tremendous amount of battery storage that's expected to come online in the next few decades. And because we've used lithium ion for most of this comes with some interesting constraints, right? Right now, there are some recyclability issues. There are some flammability and safety issues for the smaller scale. Great engineers are working on that, and they're getting better with every version. But given how much of this technology we need, it'd be nice to have some other options. So one other one more thing. Sorry, got ahead of myself here. And this is actually an image of the world's largest battery at the moment, right? This is in California, and this is 350 megawatts and 1,400 megawatt hours of storage. So what that means is when this is fully charged, it can provide 350 megawatts for 4 hours of continuous output. And this takes up about 2,000 acres. So this is a pretty large footprint, but this is what a battery power plant would look like and what we're currently building in a few locations. And so to give you a sense of how much we have in the US, so again, this is one of those facilities, 350, right? So where we are now, we're about to 4,000 megawatts, right? So this number keeps going up and up as we get further, right? Oh, nope, that's wrong. This is in kilowatts. Sorry. Anyway, on to the next thing. And where are these located? So most of the installations have been in California, in the PJM markets, right? But they're starting to pop up in other locations as well, right? So we've got a fair amount in Hawaii and Alaska as well, right? Okay. So, well, if we're going to be using lithium ion for all these electric vehicles, are there other options that we can use for these large scale power plants? So one that you may not have heard of are redox flow batteries. And what they do is they use a new cell type that is common for a few other systems, right? These come up in waste heat harvesting, water desalination, and electrical energy storage. And so what they are essentially a system that uses a pump and it has a solution. The solution is what dictates how much energy you can store, right? So imagine if we have a tank, it's usually some salts and water and some metal complex. The one I'm showing here is vanadium, but this also works for a wide range of other chemistries like iron. There are some zinc-based ones. And how this works is that in this tank, the larger the tank, the more energy storage you can store, right? This in the center is called the power cell. So you have two tanks. One has the positive electrode, electrolyte, and the other contains the negative electrode, electrolyte. You flow both solutions into this power cell, and then, like a lithium ion battery, you let the electrochemical reactions occur, it completes a circuit, and this allows you either produce electricity from by consuming the energy stored in the chemical energy stored in these electrolytes, or if you switch the direction of the current, right, with an external source like a solar panel, then you can charge these tanks. And what's unique about them is that unlike lithium ion batteries, the amount of energy you can store is decoupled from how much power you can produce or store, right? So when we were talking about megawatt hours, that means how big is the tank? When we're talking about megawatts, that's how many power cells we have. Another advantage is that we can use different supply chains than what lithium ion can use. So, for example, if we are busy using all of our lithium and copper supplies for making electric vehicles, these batteries for the grid, we can use water-based systems that use different chemicals that may be safer and also cheaper, although they'll be much heavier, so we can't put them in an electric vehicle. But they provide an alternative solution for this grid scale electrical energy storage need so that we can do both at the same time without overlapping the supply chain, well, minimizing overlap in the supply chains. So the one that I showed you here is a vanadium redox flow battery, but there are many others. And some of the advantages of using a flow battery are that the costs at scale are much lower. So comparing to two of the more mature lithium-ion batteries, this is a cobalt-based lithium-ion chemistry. This is an iron-based lithium-ion chemistry, right? So iron being less of a critical mineral compared to cobalt and manganese, the cost is much lower for large-scale storage. Whereas we look at the conventional redox flow battery, this is the vanadium-based one, it's still much lower, which is actually on par with hydrogen. Although the caveat is that you do not need a large underground storage facility for the redox flow battery. So the actual footprint of the redox flow battery is much smaller and at the same price, right? And some of the reasons for these low costs is that the simple design allows them to last much, much longer. So they have a longer lifetime. longer cycle life, even though lithium ion is still improving each year. You can do 100% depth of discharge, and they have much higher safety standards. Because they're water-based, they're less likely to heat up and less likely to be flammable. So when you're thinking about these massive battery power plants, having something that has intrinsically better safety standards in terms of low flammability and less toxic materials can be a benefit. Granted, both are still valid options, but if you can provide an alternative technology to do something similar, whereas this one is primarily going to be used for electric vehicles, there can be some benefits there. And so what these look like, these are actually also very big, right? So the world's largest flow battery was connected in China. This was in 2022. And the first version of that, which what you're seeing here, was about 100 megawatts with 400 megawatt hours of storage. So what this means is that when fully charged, it can provide 100 megawatts of electric power for up to 4 hours. And so here you can see the tanks. This dictates how much storage we have. And then over here, you're getting a visual of the power cells that are telling you what the total power capacity is. So future plans they have are to essentially double both the power capacity and the storage capacity of this site. But this is giving you a sense of what these power plants, these batteries, the size of buildings look like, right? So both flow batteries and lithium ion have been demonstrated technologies, and with future innovations, we'll see where they go. But they don't always come in such a large scale. Sometimes they can also be lower, up to 500 kilowatts. Again, this is a 4-hour storage option. And so what this looks like is essentially 40 foot. So like those shipping containers you would see in the back of a semi truck, or they'd be used to ship things overseas. A few of those, about 5, can get you this with some of the more mature technologies for a flow battery. So the spatial requirements are still scalable, and they still have that modular battery concept where you can just add more power cells or increase the number of tanks. But this can give you a sense of the scale that these batteries can take up, or at least the range where they're applicable, right? So this is still much larger than what you would need for backup power in a house, but this could work well for an industrial site where you want a sizable amount of energy available. One of the downsides that this technology has, flow batteries are even newer than lithium ion in terms of their development as a technology. So they still have some efficiency issues, but most of this is lack of research and development. So with that, I'm going to finish up with some of my work in this space. What we want to do is the first part I'll talk about is how to make these redox flow batteries better. So this is a research project with one of my graduate students where we're essentially working on trying to see how to improve these flow batteries over 3 different scales. The first is we talk with small simulations, right? So atomistic simulations to understand why these are inefficient and if we can find better electrode materials. So what we use to do this is we use a model that allows us to look at the active sites, or these are where the reactions happen on a battery electrode, and see what chemicals would work better or worse on those sites. So the current standard practice for flow batteries is to oxidize the sites. And what we did is we created an atomic simulation of what that oxidized, surface site looks like. And then we looked at another option, which is an unoxidized surface, and we wanted to compare to see which was better. So what we did is we took those 2 sites, we took our molecule of interest. This is the VO2, one of the key reactants in a vanadium redox flow battery. And we tried to see, can we get favorable bonding with that active site? And then we took our unoxidized material and did the same thing. And what we found was there's no clear absorption on the oxidized site, right? It was more difficult to get it to react with the electrode. Whereas when we moved to the unoxidized site, we found for a much more favorable connection to the surface. And so what we wanted to say is, well, that works great for the simulations. Can we find a way to demonstrate this with an experiment? So next, we moved to a miniature flow battery. So this is one that we developed in our lab. And we developed a new test procedure to try to analyze, well, how good is the positive electrode and the negative electrode doing as far as contributing to better or worse performance in the battery. So we can essentially oxidize or not oxidize each of the electrodes and monitor how they're doing inside the battery while it's operating. And so the way that we measure inefficiencies in a battery, or one common method, is what's called overpotential. So what we do is we take a battery that's not being charged or discharged, right? It's sitting there. And then we apply a current, which is essentially charging. And this eta value, which is what we call overpotential, any voltage above this line is an inefficiency. So what we would want for an ideal battery is when we are charging at a higher current, we essentially get a very similar potential as we would when we're not using it. And so the overpotentials come from a bunch of different sources, but the two that we're going to look at for this study is essentially the overpotential coming from the negative electrode inefficiencies related to those active sites that we were stimulating, and the positive electrode. Right? So before this study, we weren't sure, and the research community was not sure, how much each of them were contributing or what electrode treatment procedures were making the battery better or worse. So we were treating them the same. But what this allowed us to do, this new method, is look through for different charging and discharge rates. This is what current density represents here. And we essentially said, all right, let's not treat the negative electrode, let's not oxidize it, and let's see what the overpotential or that inefficiency looks like in both charging and discharging. And then when we oxidized it, we saw a dramatic drop, which is a good thing, indicating that the negative electrode prefers to be oxidized. Right? But when we moved to the positive electrode, which is the one I showed for the simulations, when we treated it, oxidized it, this is the overpotential level, right? That's current practices. And then when we didn't treat it, it actually dropped down a bit lower, right? Suggesting that this positive treatment, treating the positive electrode by oxidizing it was not benefiting the battery performance. And so then what we did next is then we did combinations of these two cells to confirm this in a battery during charge and discharge to show that treating the positive electrode translated to a larger overpotential, which increased the energy loss, right? So we can now use this technique to go further to try to identify what treatment methods are working best for which side, which can be a real benefit to this technology. But that brought us to another question, which was, how would this benefit these grid scale batteries, right? We know they're inefficient, and we have some ideas for how to make the electrodes better, but how much better can these batteries really get? And so because it's a new battery, much of their energy storage density, unlike lithium-ion, has yet to be really analyzed. So we created a simple model where we took 5 different input parameters that are important for battery operation. And then we created a profile to get a sense of where were we losing energy storage capacity, right? So some of it was from those energy efficiencies in red here from the overpotential. And then some was also due to the cutoff voltages, or basically how far we were pushing it in each direction. And so this told us, at least for this system, there was quite a bit of room to improve. And so we did this for a range of different batteries. And what we found is that most of these flow batteries don't even use 60% of their total capacity. And some were much, much further away with large energy storage capacities. So for this large scale, it's telling us there was a lot of opportunity for research and development to try to make them much better, right? And what this correlates to now is even though they are cost effective, right, even despite these inefficiencies, if we do more research and development, there's an opportunity for us to make them even better and make the volumetric footprint, right, like how big this building needs to be, considerably smaller. And just to give you a sense of where they're at now, so that commercial VRFB, this system, that flow battery system, this is about how much space they take up, whereas this is how much space is taken up by a lithium ion, which is surprising, but most of this excess space comes to the safety requirements for handling lithium ion. So it is possible that with further improvements in either of these technologies, we can still significantly reduce the volumetric footprint for these batteries. Okay, so I've got one more topic for you, and then I'll stop for questions. So what I've shown you so far in this presentation has been electrical energy storage, but my research group is also working on another new one. So this is a form of a flow battery, but instead of charging it with electricity, this one can be recharged with low-grade heat. So what is low-grade heat? Well, what we classify that as something about 100 C to 200 C, which is most of the waste heat that's produced in the US. So if you think of all the power plants that we're using today, petroleum processing, factories for making glass and cement, factories for burning waste, most of that we use to produce energy or consume energy in terms of thermal heat, most of that is lost. Only a small fraction of that actually goes to driving the processes that we want, right? So about 32 quads in the US, 65 of that goes out of whether it's a smokestack or a tailpipe in these different temperature sources. So even if we're able to improve the efficiency a little bit, this can represent a large opportunity. But small temperature differences have been notoriously difficult to harness. So what we're working on is taking the flow battery technologies that I showed you before and coupling it with a thermal separation process to allow us to try to use a flow battery that can be recharged with waste heat. And so how does that work? Well, what we do is we identify species where if we take one redox reaction, this is something happening at one electrode. If we add a species like ammonia, it can change the potential, allowing us to harness a potential difference between the two electrodes. But if this species can be removed with heat, then we can essentially find a way to add it to one, harness electrical energy, move it out. And so the way that this would work is like this. We have a flow battery where ammonia is on one side. The potential of this is about 1 volt different than this side. We produce electrical power until the two sides match, or we're not able to anymore. Then we take the spent solution, put it into a thermal separation process. And what we found is that by adding about 90 C worth of heat, we can drive the ammonia off, which produces the solution that was used on the other side, giving us a pure ammonia stream. When we add this to this new side, we can recover the battery and return the cycle to start. So although the efficiency of this is low, what this allows us to do is produce electrical energy from chemical energy. Once that has been consumed, we add it and we recover that chemical energy by adding thermal energy, right? So moving ammonia is the energy carrier from one side to the other. And so there are other technologies that have used this. The one that we've used in our lab has had the highest energy density so far. So this is about 10 watt hours per liter. This is low for a flow battery, but very high for waste heat recovery. And the two metrics that they've cared about for this type of system is the round trip efficiency and the power density. So these new aqueous trabs that we've worked on for this, which is this technology that represented the highest efficiencies in this space. So if you think of like a thermoelectric generator, these are actually about 1% efficient for these low temperature differences. Ours are getting closer to, I think, about 50 to 60% of the Carnot limit, which is some of the best performance in this space. Given the early success we had with this, we looked through different membranes and we tried to identify what the cost of this new system would be compared to something like the flow batteries that we've used before. And so even for these early prototypes, what we found that we're getting quite close to being competitive with the commercial VRFBs so far. And if we keep making improvements, there's a potential for them to be even cheaper, which was encouraging for us to further develop them. So now we are exploring new architectures to try to better optimize this process. So this means new separators, which we've found to have a huge impact on how much power we can produce. We're starting to do durability tests to see how many cycles we can go without performance loss. And we're looking into the thermal charging process to try to see how fast we can charge it. So our next target is an organic Rankine cycle, which is used a lot with geothermal energy. That is our next target for this technology to try to make it competitive with that, which we believe is the major leader in this space. All right. So I'd like to thank everyone for listening to my talk today. I'd like to acknowledge my collaborators. So these professors through a wide range of different universities at Penn State, KAUST, George Washington University were extremely helpful in a lot of the research that was I presented here today, at least in our portion, and especially the graduate researchers and their work to help us here today. So Ronaldo, Nicholas, Jose, Ridge, Callaway, Tim, each one of them had contribution to some part in this the small bit of research that I showed you. And so thank you very much. If you want more information about anything I talked about today, here's my contact information. With that, thanks.
Thank you, Derek. Very interesting. I think Chuck and Joe are going to read through the questions.
So thank you, Derek, for that wonderful, wonderful overview of all the value and battery technologies and all the hope for the future and opportunities for grid level storage, which has been a holy grail for a long time. So I guess the first question is, hello, everyone. Please, can you send your, did the battery development result from market demands or government funding, grants, and directives? This is the early work, I think, of electric vehicles back in the 1850s. I think that's what the question's relating to.
The very early development, I think, was scientific curiosity. The start of lithium ion, I think that's a better example. A lot of that was pioneered by Sony, and I think that was for their personal battery space, right? That's when personal electronics were taking off. So a lot of that was market demand. But a real answer to that question is complicated, right? Often they're so mixed, it becomes difficult, right? A lot of fundamental work by scientists have been funded by government, and then industry tends to swoop in once it gets close enough. So it's usually a bit of both, I would say. But at least for lithium ion, the first ones came out of Sony, not out of a government lab.
Joe,
Okay,
let's get this.
Sure. The next question is, I understand economies of scale resulting in the price of lithium batteries decreasing. Is it foreseeable down the road that the cost of the supply of materials, both by natural causes such as mining costs and human imposed, such as legislation, causing the cost of lithium batteries to actually increase?
Yeah, so that's a good question. I do not have a crystal ball. I do not know what will happen next. But those are two excellent points. Those will likely increase the cost, at least up front, right? Legislation can do all kinds of crazy things, both good and bad. But the mining and material acquisition side is an interesting one. So mines take a lot of investment up front, but when they're run, they can be managed cost effectively. So I don't think in the long term the cost of mining will go up, but the investments needed to get more mines up and running, that's definitely a concern and something that a lot of researchers are actively looking into.
Derek.
Some room for those prices to still go down in spite of that is that I mentioned a bit about different supply chains for different materials, right? Cobalt being and manganese being two really popular ones that are brought up a lot. There are lithium ion and other battery chemistries that don't use them at all. So some of these technologies some of these suppliers will start to switch to different battery chemistries depending on the lead and the lag in the particular chemistries they're using. One good example is lithium iron phosphate. So that minimizes a lot of the critical minerals that are in some of the other high performing batteries. Their performances are similar, so it's not night and day difference, but it will change your total drive time a bit. So I think there's going to be a lot of shuffling as some mines start to come through and some of those complexities that you mentioned come to fruition. But I think there's enough wiggle room in the chemistry and the different options that I think the prices will still go down. But yeah, I would
Is
be a
the iron
market analyst if
phosphate
I was great at
safer?
predicting the future. What?
Is the iron phosphate safer?
They've also been shown to be safer as well. But again, the technology is changing so much. There's new research coming out that have been working really well with the traditional cobalt-based chemistries and minimizing a lot of their degradation. So because it's a new technology, it's constantly getting better. So yeah,
So that piggybacks
what was
on,
right a couple of years ago has been wrong, and then it goes back and forth. But typically, lithium iron phosphate has been a bit lower energy density, but more safer and easier to identify the materials.
so that piggybacks into this question really nicely. What about the potential for compressed energy explosions in lithium systems?
So there are definitely safety concerns with lithium ion batteries, but it also has one of the most rigid safety standards for their production. So there are a lot of inherent both controls based and materials based safety procedures put into building lithium ion batteries. And some of that solid state battery technologies that I talked about provide other opportunities to minimize the risk for potential catastrophes with those batteries. So lithium is a very reactive material. Just like the gasoline we put in our cars, right? There has to be certain safety procedures in place. That's always going to be a reality with high energy systems, right? That's sort of innate to the process. But engineers have been very good at managing those safeties in the past, or finding new and creative ways to make them better. So I'm confident that as we make more of these and as we use them more often, they will keep getting safer. But yeah, again, anytime you're working with a high energy system, there will always be rooms for concerns. And this is the same with coal-based power plant systems, natural gas systems, any of our pipelines. That engineers always have to look about safety, right? Because these are very dangerous materials, right? That's just a reality.
Okay,
Joe?
Two questions actually. How are new battery ideas fostered and seasoned in your program? And the second question is, are there standing design objectives for battery research? And furthermore, if possible, can you please compare and comment on lithium iron phosphate batteries?
So new battery ideas. That's a good question. Yeah, I don't know where the new ideas come from. Because if I could figure that out, I'd make them come more often.
Probably at 2 a.m., right, Derek?
What?
Probably happens at 2 a.m. An
Right.
idea pops in your head.
So a lot of the new ideas come from us talking. Like, we have professional societies where we talk about different battery ideas, where the problems are. We look at different fields that have solved some similar issues or related phenomena, and we try to look for cross-connecting ideas. So some of the interesting things that have been going on in batteries lately, right? Most of the issues we've had with lithium ion have been chemistry issues. Like, can we find the right chemistry that has good energy density, has the right degradation properties from chemical degradation? But most of those are chemists. They're not good at heat transfer. So now mechanical engineers that are good at heat transfer have redesigned the battery packs to make them safer, which they would consider to be intuitive, right? So as they become more popular, more experts work in them, and someone from a heat transfer expert would look at it and go, "Oh, this is obvious. Why don't you have your tags all the way around rather than in one spot? That's going to minimize your heat transfer." And then the chemist is going to go, "Yeah, I had no idea. Great." So a lot of that is working in teams, getting new perspectives. Standing design objectives. So we generally have some like overarching things that we're trying to attain, right? So like energy density, right? Like how much energy can we store per unit of mass? Those are targets, like in that slide where I was showing the new technology, right? There are targets by the government and by certain program or certain companies where they know if they can reach that number with a different material, then that's going to be helpful, right? So it's like cost plus energy density or power density numbers give us a sense of, is this a good idea or a bad idea? So that would be an example. That would be my thermal regenerative flow battery. I have to look at competing technologies like the organic Rankine cycle, say what is their efficiency, what is their cost to produce power, and then those are the markers that I use to try to develop a new technology or figure out if a new idea is a bad one. Next one was lithium iron phosphate versus I think like the normal NMCs. Yeah, so that's an interesting one. The lithium iron phosphate is a newer chemistry that's starting to be adopted in electric cars. And I think some of this has to do with supply chain issues, right? So or anticipated supply chain issues with nickel, manganese, and cobalt. But depending on the need, they've gone back and forth. So I don't really have the expertise to comment on those nuances. You have to be really entrained in that area and how they're developing to give a good opinion. So I just sort of know the overview and what I learn when I go to my meetings, but I'm not trying to make a better lithium ion battery, so I'm not the right person for that. But
So
I know
this
they
next
both work
question.
great in different scenarios.
So this next question is, which scenario are you most excited about, transportation or storage?
Um, for me personally, I think these power plant batteries are really exciting to me.
Yep.
The market's smaller, but what that does is that enables like us to take all of the electrical energy production and make it more sustainable, right? So all these electric vehicles, if we get them, we need a clean source to reduce their emissions, right? Because if it's all powered by coal or natural gas, then we're just like offsetting the emissions somewhere else, right? But if we can connect grid scale storage with solar, this can provide a real opportunity to make everything lower the emissions of a lot of different sectors. It's also more challenging and interesting because the design marks are different, right? So in a car, you really care about how much energy you can store per unit mass, right? Because you need to move the battery. So whereas if you're a building, the how heavy it is less of a concern. So it opens up a lot more possibilities, right? You usually care about how much space it takes up and how much it costs and how long it lasts, right? Um, at least as far as conventional power generation logic goes, right? I mean, there's still some mass constraints, but it's much, much less important, right? The one analog would be like the rocket fuel problem. If your fuel is really heavy, you need more fuel, and it makes it very inefficient, right? Well, we don't have that problem with grid scale storage, which means that water-based systems that would seem ridiculous for a car, now because of the safety and the cost become really interesting options. And the reason I'm also excited for that is that's also a very new problem. Having excess electricity is a very new problem, right? Trying to come up with grid scale energy storage was not really a high priority until you have an intermittent source of electricity. So
Right.
yeah,
And it's going to grow in leaps and bounds as we move towards electrifying everything we can.
right.
Joe, you got the next one?
Sure. What about the environmental impact of each type, and where does that fall in the analysis?
Yeah, I think this is a really important issue. Um, the the one major challenge with these new battery or any new technology is how do you recycle it, right? So the one good thing about a lot of these batteries is that it's solid waste. So unlike fuels, when you burn them and you have a gas waste stream to deal with, the size and both the handling of a solid is much easier, right? So the good news is that the waste will be localized, will be solid. The downside is it's an entirely new problem, right? Um, so if you look through the history of human interactions with energy, every time we find a new energy source, there ends up being a recycling or a sustainability problem. So we went through this with wood, we went through this with whale oil, went through this with coal, natural gas, petroleum. Each one provided a new we call it like closing the loop on that. So that's really important for batteries. There's a lot of government incentives into trying to find solutions for that, and there's a lot of active research in that area because just trying to find new minerals all the time isn't practical. And honestly, as humanity increases, it's just not a practical solution, right? So I can't say comment on each of them, which one has more or less of environmental impact. It's not my area of expertise, but what I would say is, well, one interesting point that I would bring up. So if you take a lead acid battery, that one is almost, I think it's like 95 or 99% recyclable. Every time they take one of those, if you give it back to the manufacturer, they take almost everything out of it and then make a new battery out of it. So there is evidence that we can figure this out, but that's where the work still needs to be. And
There are companies developing this. I mean, there's a number of startups that are involved in recycling lithium-ion batteries.
yeah, it's a huge area of research interest. Over the last few years, the number of opportunities to work in that area has just exploded.
What about flow batteries in home energy storage systems?
Hmm.
Yeah, so this is I don't have a good answer. Someone asked me this. It seems like it would be reasonable, but it hasn't happened yet. So it's probably a good reason. I just don't know what it is yet.
Would
My
it be
best guess,
space, Derek?
What?
Would it be a space problem?
Um, it could be, but Um, I think it's just the scale at which these work well for so far. But
Mhm.
honestly, I'm not sure. I mean, they do take up more space, and people have an issue with that. But these batteries aren't particularly large. I mean, the commercial side, when doing them safely, they're fairly close. So it's not like you'd have a flow battery the size of your house to support your house. It's not that bad. But yeah, I think it's just too new and like most of the companies that are starting in this space, they're very young. They're targeting the huge scale because the market's there. It's robust, and the utility companies are more likely to invest. So I think if you're going to build up the production capacity to do this, it makes sense to target the larger one first. I think that's mostly it. Is they're new, and they're going to go where the biggest pot of money is. Whereas lithium ion is kind of the opposite, right? They started really small first, so they've got that down already. But I mean, that's my best guess. I'm not too sure yet. Nothing obvious has jumped out other than that it's new.
Yeah,
And the next question, what kind of separator, how large, and how many?
I have no idea the context of that question.
I don't even.
Candace,
Well,
do you want to
so
just, Candace, can you just tell us what you're thinking?
Elaborate.
Is she here? Just unmute yourself, Kansas.
Solar power.
Candace,
Oh,
there
yes,
she is.
it has to do with solar power,
Solar power.
Solar power is separating
separating
oxygen and hydrogen.
oxygen and hydrogen.
hmm. um,
That would be electrolysis.
yeah.
Yes.
So the separators, usually for like a electrolysis, at least there's a couple different technologies you can use. Most of them use some sort of ion exchange membrane. You can even use reverse osmosis membranes to do it to separate them. So they're usually some sort of polymer that's a few microns thick, and then the area, it sort of depends on the reactor size that you're looking at. So the good news about PEM fuel cells, sort of like batteries, and also the flow batteries I showed you, is they're modular. So if you get one reactor size, like the one we have in our lab, it's maybe I'd say maybe a foot by half a foot, and they build that, and then they just repeat that over and over again in these little modular cells, and each one's its own fuel cell, and they connect those up to make whatever size you need. So the number really depends on how much you want to do, right? So like if one of those is produces a certain amount of hydrogen, you want more, you add more. Yeah, so usually just one type, and then because that membrane is the most important, after that, once the fuels go into the outlet, they go into tanks, and then hopefully they never see each other again unless they're supposed to. But that separator material, it's usually we call them high performance polymers, where they're holy, but just holy enough so they only let the right things through, but not the others. And almost all of these technologies have some form like that. So lithium ion the current ones have a polymer based separator, right? There's small holes to stop one side from touching the other. The flow batteries I presented, they have them as well. And there are 6 or 7 types with different chemistries, and they have their advantages and disadvantages. But the one thing they all have in common is they're usually polymer based, and they're usually pretty thin, and they follow this modular design.
That's it for
Okay,
the chat.
we have, thank you, Split. Thanks for all the information. I have a question for you, Derek, which just relates to this solid battery at the bottom of your future battery types, which has 5 times the energy density. What is that?
So those are some of the new solid state batteries that have been developed. So they sort of use like lithium metal batteries, where that's sort of a very high energy density material. Um, and then on the other side, they just use air. So it basically like minimizes how much material is there, right? Think of it as like a battery that breathes, and it's like those are the ones that they're referring to there, right? So it's sort of like lithium metal They have some sort of separator and then oxygen. I'm pretty
Okay.
sure, but again,
Okay, so these are metal air
I'm an expert too.
batteries, similar to the zinc air batteries, only with lithium.
Yeah, and some solid state separator between them. I
Okay.
think those are the ones, but that's my best guess. If we go back to the link, you can find it for sure. So
That's
there's a
great.
really good review that came out recently on the different versions. Even the inventor of the first lithium ion battery, he had a version of this that came out a few years ago that they were working on. So it's a really new area that's exciting. Each one's a little different than the others, but I think they were a lithium. Let me just look back to double check because I think that was the case study that they showed. It was like the potential of one experimental version of lithium air. Let me see here. 2 seconds. Yeah.
But that would really change the footprint for grid storage.
Oh, right. Absolutely. But I'm still sort of an advocate of, we've got so many transportation systems, and that's such a large chunk of our energy supply goes into transportation. I think all the lithium should do that first, and if there's any left over for the other ones, go for it. Yeah, so lithium air solid state cell experimental results were about 600 watt hours per kilogram, which is about 6 times what the original Sony battery did, and about 3 times what the current state of the art's doing. So it's an early technology, but it's really fascinating, right? So it's sort of the solid state's kind of trying to take away some of the inherent dangers with lithium metal, like the dendrite formation, which leads to the same thermal runaway problems they would have if another one. But the best
And the
part about
electrolyte.
using a metal-based battery is it's super dense, a really high energy, and if you're using air on the other side, air's everywhere. That's a strong benefit. But there's been a lot of safety and performance challenges with sustaining that. But the new solid-state batteries look like they're starting to move that way. And the fact that some companies are willing to produce it's also helpful, right?
Great. Is there anybody that has a question that wants to unmute? We're coming up on 8:30 here. So just anybody want to ask a question before I thank Derek again for a very informative and interesting survey of battery technologies. Going once, going twice. Oh, Ruth, yes. Oh, she's clapping. Okay. All right. I think Derek will say goodnight. Everybody's clapping, smiling, sending emojis, I think they're called. So thank you very much, Derek.
Yeah, great
Thanks, everyone.
presentation,
Appreciate you
Derek,
listening.
and really thank you for your time tonight.